Okay, kids, today, like I said, I don't think we'll get through everything. My goal is to kind of get through the vocab in example 3 today. If we accomplish that, that'll be a good day for us. And then here's the deal. After I get done with work today, I won't make you do anything for the rest of the year. Okay? Sound good?
That's so sweet of you.
Guys, 4.2 is titled Properties of Rational Exponents and Radicals. And we started exploring some of these new ideas the other day. Hi, what's up? A shaker.
Which color?
Orange if you've got it.
No, we got red.
Red'll work.
What is this for? I don't know. I'm just supposed to hand them out.
Merry Christmas, y'all. Merry Christmas. Cha cha cha. You like that one? Okay. Actually, we could explore why that's doing that right there and talk about the elliptical sections of that, and we could use calculus to determine where the center of gravity would be for that thing right now. Shall we?
Yeah.
Well, can you do the stuff inside of it?
What about the stuff inside of it?
No,
Well, yeah, we could cut it out. We could figure out where the center of gravity is, though, based on the angles at which it's laying and based upon all the elliptical properties of it.
That's too much.
You don't want to do that. It's just a lot of integration, finding antiderivatives of functions that we would come up with. It's pretty simple. Or do you want to stay? I have any clue what you just said. All right. Okay. Hey, let's get rolling back on this right here, guys. So what we're looking at today is 4.2 properties of rational exponents and radicals. And like I said, we touched upon this a lot in the first section. I think you guys had a really good understanding of what was there. I really liked the work that you did there in the first section. So today, things are going to get a little bit more complex as we start looking at this. But the question that we're trying to answer today is this. How can you use properties of exponents to simplify products and quotients of radicals? Okay, so some multiplication and division ideas are going to show up here today. All right, so our goals today, my friends, we're going to look at using properties of rational exponents to simplify expressions with rational exponents. Again, that word rational typically means what, guys? What's another word I said you could think of when you hear rational? Starts with an F. Sounds kind of like rational. Fractions, yep. Think fractions. Okay. The second goal today is to use properties of radicals to simplify and write radical expressions in simplest form. This part right here, guys, this is not very easy to do. This is kind of tough on kids at times. So we're going to really dive into this and make sure we've got a great understanding of what that means. So let's establish some vocabulary first, guys. First thing that I have is called simplest form of a radical. Okay. Simplest form of a radical is an expression involving a radical with index n, and it's in simplest form when these three conditions are met. It says no radicals have perfect nth roots or nth powers as factors other than what? 1. Okay. No radicals contain fractions. All right. And no radicals appear in the denominator of the fraction. You can never have a radical in the bottom. So let me just give you an example like this, kids. I'm just going to use a simple one, square roots, because we're going to get more involved with this right here. But let's just say I have the square root of 8 right there, okay? An example would be like this. Think about perfect squares. If I had to list perfect squares, 1 would probably be the first perfect square. What's the second perfect square? 1 would be a perfect square because 1 times 1 would make 1, right? What's the next perfect square? 4, because 2 times 2, and then the next one would be what? 9, 16, 25, and so on. And we'll start looking at perfect roots here in a bit. But guys, think about that square root of 8. Okay, looking at that value of 8, is there a perfect square that I could use to factor out of 8? Which one of these numbers besides 1 would go in there? How many times? So this is like saying, well, this is like the square root of 4 times the square root of 2. But my friends, what is the square root of 4? 2. So we would call this 2 times the square root of 2. And my friends, this would be simplest radical form right there, okay? So we're going to be trying to take out perfect nth roots if we can. And I'm going to just make the note here. You're always trying to take out perfect nth roots. Okay. So that's the first thing that we're going to talk about vocabulary-wise. Second one we've talked about a lot, especially when we dealt with polynomial functions in Chapter 3, a conjugate. It says the expressions square root of b plus c times square root of d. And I think I've got a typo here. See this c right here, guys, in here? Change that to a b right in there. Okay, you see that right there? Okay, it says the expressions a root b plus c root d and a root b minus c root d are conjugates of each other where a, b, and c and d are all rational numbers. So let me just give you an example. So suppose I have something like this, 3 root 7 plus 6 root 2. Okay. Basically, my friends, same expression, but the plus sign would be what kind of sign if it was a conjugate of that expression. Minus sign. So a conjugate of that would be 3 root 7, not plus, but what, kids? Minus 6 root 2. So we've talked about conjugates often. I think you know what those are. Okay? All right. You're going to hear me say like radicals. All right? Sounds like the name of a new band, the Like Radicals. Okay? Radical expressions with the same...
Sorry for the interruption. There is a silver Chevy Impala in the parking lot with its lights on. A silver Chevy Impala, I think in the first or second row with its lights on.
Probably Jalen. Okay. Okay. Radical expressions with the same index and radicand are called like radicals. So let me just give you an example here. If I have the second root of x plus the second root of x, do I have the same index on those, guys? Do I have the same radicand, the part underneath the radical sign? So how many of these would this equal? 2 square roots of x. Okay. Like radicands are almost like the following, guys. They're almost like terms. Like, you know what I'm saying? Like gnarly. Like radical, dude. Okay. What, is there a text already?
No, I'm just wondering because my dad says we have this like fun practice and I'm terrified for my life at the moment.
Oh, really?
Yeah. And
It's
he won't tell us what it is.
Fun, a different definition.
And Bart's vocabulary, it's like he's probably gonna try to like kill us or something.
Fun for him, right?
Yeah.
All right. Properties of integer exponents, kids. Properties of integer exponents. We'll talk about that. I want to look at the next page here real quickly, guys. I want to see if this pops up here again. No. Okay. I'm just going to write this down here. I'm just going to say there are many rules with properties of integer exponents right here, guys, but the thing that we're going to see the most is 2 of them. A lot of multiplication and a lot of division. But if I had integer exponents like this, guys, if I had like x to the third times x to the third, what would that equal? Or what do you do with exponents there? X to the 6th. Okay, that makes sense to you? Okay. And then if you have something like this, like x to the 7th divided by x to the 3rd, what would this equal, friends? Yeah, you've got 7 x's up top, 3 x's on the bottom. So really 3 of them are going to be taken out, both the top and the bottom. This would be x to the 4th. So we're going to talk about those properties of integer exponents. When you're multiplying like I am on the left, what do I do with exponents to form x to the 6th? Okay, and when you're dividing, what do you do with exponents to form your exponent on the right? Subtract. Very good. Okay. Guys, you're going to hear me talk a lot about rationalizing the denominator. Sometimes we're going to have some expression up here. I'm going to have like a question mark up top here. We're going to have like a square root of maybe 17 down here. Okay. Now, rule examples of writing things in simplest form. Whatever reason, and I'm not really sure with this, they don't like irrational values in the denominator. So when we talk about rationalizing a denominator, friends, what we typically do is we say, well, if I've got a square root of 17 down here, we multiply by another square root of 17 in this form of 1. Because isn't root 17 over root 17 equal to 1, kids? Okay, if I times something by 1, am I really changing it? No, okay. So guys, when I do this right here, suppose that I had like 3 root 5. Is 5 a perfect square? No. If I had 3 root 5 as an answer, I would say I need to rationalize this. Rationalizing means you cannot have the denominator have a root in the bottom. You've got to have some kind of an integer down there, okay? So what we do here, guys, is we say, well, let's multiply in the form of 1 by root 5 over root 5, okay? What's that make up top? Well, that would be 3 root 5. Guys, talk to me about root 5 and root 5 right here. What would this 5 times 5 going to make? Root 25, but 25 is a perfect square, isn't it, friends? Yes. So what is a square root of 25? So this is really 3 root 5 over 5. Do I have a square root in the denominator anymore? No. So what we've done right there is called rationalizing the what? Denominator, okay? Guys, y'all know what absolute value is, right? Okay, it's just like an
There's no school.
expression.
Text.
Aw, I'm gonna miss you guys.
I don't get those texts.
We'll miss you. I do.
We'll miss you too, but
I'm sad. No, you're not. Okay.
Talk about this since Monday.
I know. Okay, I think I even said something about Friday. Okay. All right. So absolute values just involve bars around them. You all agree with that? Okay.
Wonder why.
oh no, not the bars.
Feels like -9.
Okay.
Feels like -9.
All y'all have the vocab down to start? Okay, let's move over here. Like I said, we'll get through some stuff here. I really would like to get through example 3 this morning. Okay. Guys, core concept here. This is kind of important for you today, all right? I would make sure you pay good attention on this. Okay? All right. Guys, the first one I have up here is product of powers. I'm going to kind of put your rule down in the middle column there. And we'll put an example next to it. So this first one right here says the following. If I have a to the m power times a to the n power like this becomes, okay, you guys agree product means multiplication, don't you? And we kind of talked about this in that part where we said, see that table over here, this core concept, this is going to be pretty important. This is going to become a to the m plus n power. So for an example, suppose I had 7 to the 6th power times 7 to the 2nd power right here. What would that equal? 7 to the 8th power. You guys know that. Okay, we've seen that before. All right. Now the next one, I think that this is a very important one right here. You might want to put a star by this one. Okay. Sometimes kids get a little lost on this. All right. This is simply saying the following. Power of a what? If you have in parentheses a to the mth power, all to the nth power like that on the outside of parentheses, then this becomes equal to a to the, yep. So I'll go back to this right here. I don't have a text. Okay. So if I had 7 to the 6th power in parentheses, all to the 2nd power, this would equal 7 to what power, my friends? What would you do with the 6 and 2 in this case? Multiply, right? This would be 7 to the 12th power. Okay. All right. Another important one, I think, is this. It's called power of a what, kids? So if I have something in parentheses like this, a times b, isn't that a product right there? And if I take that to the nth power like this simply becomes the following. It becomes a to the n power times b to the n power. So I'll give you an example here. Maybe you have, isn't 2x a product? 2 times x, kids? And I take that all to the 5th power. Okay? Well, kids, this is going to become the following. You would bring the 5 into the 2, and you would bring the 5 into the x like so. So this would be 2 to the 5th times what? Okay. Now think about that 2 to the 5th part. Can that part be evaluated? Can I take 2 times itself 5 times to get an evaluation there? What is 2 to the 5th power going to be? Okay. So 2 times itself 5 times would be, did you say 32, Hamed? So this would be 32x to the 5th there. Okay. All right, first 3 core concepts, you have them down? Okay. All right, negative exponents. I think another one that's pretty important. Okay. If I have a to the negative n power, and we kind of talked about this the other day, this is the same as 1 over a to the n power. Okay, so like this, if I have, I don't know, x to the negative 3 power, this is the same as what, kids? 1 over x to the, not negative 3, but, okay, let's squeeze that in there. So x to the positive 3. I hear a big old choo-choo train.
I think they're watching Polar Express.
Sounds like it. Okay.
Polar Express is too generic. That's the right
You're
word?
generic.
It's just like
Take a seat.
I
Is that
agree.
a three? With your ego.
Yeah, over x to the positive 3. Okay. All right, 0 exponent. Anything to the 0 power with the exception of 0 would equal, anybody know what any of the 0 power is based upon? It's 1. Okay, so if I have, I don't know, 9 to the 0 power, what's that going to equal? 1. Okay. I will say this, though. A cannot equal 0. Okay. Quotient of powers. We've talked about this already. Okay. Suppose I have like a over b all to the nth power like that, kids. Anybody want to guess what this becomes? A to the n divided by b to the n. So suppose I have 2 over x to the 3rd power. Okay, that would equal 2 to the 3rd up top. What is 2 to the 3rd? So up top you would have 8, and then how about on the bottom? X times x times x. What would that be? X to the 3rd. I'm running out of a little room. I'm going to squeeze it in there. Can you guys see that that's x to the 3rd okay there, guys? Okay. And then finally, oh, I messed that up, you guys. Change that one up here. Switch these around right here. Power of a quotient and quotient of powers. I messed that up. Okay. So actually, let's do this. Let's make the arrow this way. Let's do it this way. This should actually be for this. I read that, misread that. That should go right down there, okay? You guys good with that? Quotient of powers should be something like this. If you have a to the m up top over a to the n, this would equal a to the m minus n. My mistake. So if I had something like this, 7 to the 5th over 7 squared, what would that equal, kids? 7 to the 3rd. Okay, so this example should go right up there. All right. Okay. Core concept. You have that stuff down there? Okay, my friends, let's talk. Okay, my example 1 here, using properties of exponents. It says use the properties of rational exponents to simplify each expression. No problem. Okay. Guys, the first thing that I have up here is a product. First of all, what do you notice about these bases right here? Are they the same or are they different? Both are 13. So 13 and 13. So what am I going to do with exponents right here when I do this? If I'm taking 13 to the third, yep. So we're going to have to, this is going to equal 13 to the 1/3 plus what up here, guys? Okay. So we've got to take 1/3 plus 1/6, right? Not a problem. We've got to get common denominators for the 1/3 and the 1/6. So this would be 13. Guys, what would 1/3 be with a denominator of 6? You guys agree with that? Okay, but wouldn't this now be 13 to what power, friends? Okay, and 3/6 would reduce to what again? So in simplest form right here, in simplest rational form right here, this would be 13 to what power, kids? Okay. You guys all right with that? Okay. Next one, we have some parentheses. I kind of like this next one. It's a pretty cool little problem. Okay. I've got 5 to the 1/5 times 8 to the 1/4. I could bring this 5 into this one and bring this 5 into this one. So here we go. This becomes 5. What's 5 times 1/5 going to be, kids? Won't that just be 5? Times 8 to what power? 5 over what?
4.
Okay, now this one here you can do a couple of different things with. I want to see how they simplified that one here. Give me a second to look at something here, guys. I'm going to guess that they called that 40 times 8 to the 1/4 power. I would hope that they did. So we're really canceled already tomorrow. Guys, what kind of fun am I going to have today, Sam, when we're here tomorrow to everybody?
Well, I don't know because only Jamie's got my text.
Really?
I have.
Who else got it?
I have the proof. I'm not making it up.
Oh, I know. I know. I'm just saying I wanted to tell everybody I think we'll be here tomorrow. And now my day is kind of ruined. Should I? So they'll all just yell at me anyway, Gracie.
Ew, you added him. He added me.
Who added who?
After I
Okay. They just leave this one as 5 times 8 to the 5/4. And you know what? I'm kind of okay with that. We can leave that right there. Can 5/4 be reduced at all anymore, guys?
No.
Probably not. So your solution right here, kids. There it is. Okay. Next one. This is a little bit interesting if you ask me. This becomes the following. This becomes 12 to the negative 1/3. We have that assembly today.
For what?
Do we just go straight to the art then, or do we go?
I think you go to the art. I don't know, Molly. Nobody's told me. I just know we're having this. Okay, guys. So right here, guys, watch this right here. We need to bring this negative 1/3 in here. So this becomes 12 to what power, kids? 12 to the negative what? Okay, times what? 9 to the what? Negative 1. Now, guys, one thing you're going to hear about a lot in this chapter is you do not want to write stuff with negative exponents. So how could I rewrite 12 to the negative 1 power, guys? 1 over 12 to the first. So isn't that really just like 1/12 right there? Times, how do you write 9 to the negative 1 with a positive power? Okay, so think about this now, guys. Could I take these two fractions and multiply them together to get simplest form? What's 1 times 1 going to yield up top? And then anybody know 9 times 12?
No, I'm not that smart.
How much?
108.
Yep. So a solution here would be 1 over what, kids? 1 over.
108.
Okay. 1 over 108.
What are you doing?
Okay. With me so far? Let's try a couple more here. Okay. I don't like the way this is written. This is like, this is really saying the same as 8 over 8 to the 1/9 power. Guys, that 8 is really 8 to what power up top? 8 to the first, isn't it? Okay. So in this case right here, you would just simply subtract exponents. So what's 1 minus 1/9 going to get? Yep. If I had one whole thing left and I took 1/9 out of it, how many of the ninths are left? So this would be 8 to the 8/9 power there. Okay. Next one. Now, I really like this next one. And a couple things I want to point out to you is this. Okay. Guys, notice right in here, inside of this one right here, what do you notice about these two exponents here? They're the same. So if that's the case, this is the same as, this is kind of the same as 56 over 8 to the 1/4 power. And then we're going to take that whole thing after that to the what? Okay. All right, so talk to me, friends. What's that 56 over 8 make since these exponents up here are the same? What's 56 divide 8?
7.
So this is like 7 to the 1/4 power. Now all to the 3rd power there. Okay? Guys with me there? So now we're going to take this 3 times the 1/4. So this is going to become what in the end? 7 to the... Okay. Okay, let's talk here, kids. Product property here of radicals. Okay, radicals are going to be anything that involves roots like this. Okay. It's all right. Guys, product property would say something like this. If you have the nth root of A times the nth root of B like this, this will equal the nth root of A times B. So for instance, if I have the 3rd root of 7 times the 3rd root of 6, this would equal the 3rd root of, anybody want to guess? Okay, so that's what product property says with radicals. So, quotient, same kind of thing. If you have the nth root of A divided by the nth root of B, then this is going to equal the nth root of A divided by B, like so. Okay, so let me just give you an example. Suppose I've got the 3rd root of, I don't know, 60 over the 3rd root of 6. This is going to equal the 3rd root of what? 10. 60 divided by 6 would be 10. So those are some examples right there with that. Okay, so let's roll on to the next page here and take a look at some examples. Oh, I'm sorry. Let me know when you're ready.
We're watching Rudolph and Mr. Klaus today. Oh my god. He sent us a snap of Rudolph.
Okay, that's the dumb Rudolph.
Yeah, that is.
I want the good Rudolph.
I want jump scare.
Good, Ava? Okay. Anybody else need more time with those? Good? All right. Everybody good? All right, my friends, let's roll. Are we on to example 2? Okay, so here we go, kids. Properties of radicals. Use the properties of radicals to simplify each expression. Okay, here we go, guys. What do you notice about the index on both of these roots right here?
The same.
They're the same. So this is going to become the cube root of, what's the number, or how am I going to get the number to go under there for a radicand? That number that goes under the root is called a radicand. Anybody want to guess what I'm going to do? 4 times what?
128.
Turns out to be what? 512. Now I want to show you something here, kids, because this is kind of a goofy thing, and I'm going to take you to this today, and we'll recall it on. What do you guys come back? January 3rd, I think. Okay, maybe we'll get another storm on January 3rd to bookend our.
I hope so.
Oh, you guys crack me up.
Oh, I remember that.
Remember that? That was crazy, wasn't it? Okay. Kids, you remember, so on the website right here, when we go online calculators and resources, you might want to make a note right here in your notes. Okay. One thing that I'm going to talk about is perfect nth roots table. Okay. There's going to be a link for perfect nth roots. Hopefully it pops up. Okay. We're going to have a table of squares, cubes. We're going to be referring to this chart a lot in the future. So, kids, the part that we're at right there, does it say we're at a cube root of what? 512. Jump in here, guys. Go to this cube column right here. What do you notice shows up in this cube column? 512. It looks like the cube root of 512 would actually be what value? 8. When you do these right here, I would always check to see if they're a perfect nth root. And we'll use this table more. But I think the thing that I just want to bring your attention to here first is this. The table in Parsons' website, you might want to write this down. Perfect nth roots table. Okay, and that's, again, right here. I'll show you where that is again. It's under here. It's under my links to calculators right here. But you guys see that perfect nth roots table length right there? Yeah. Okay, we're going to be using that a lot. So just make sure you know how to get there. It's with all the other resources that we've used so far in this class. But, guys, it turns out if I would actually punch in the cube root of 512, let me do this real quickly. What's it equal? 8. So cube root of 512, that's pretty good, but we can simplify that down to be a nicer answer and just call it what? Well, it's equal to 8. Okay. Kids, this next one right here, which root am I looking at for both of these? 5th root. So since those roots are the same and it's a quotient, this could simply be the 5th root of whatever 192 divided by 6 is. So let me do this. 192 divided by 6. What value is that? 32. Well, lo and behold, my friends, let me write this down. This is the 5th root of 32, but it actually turns out that 32 has a perfect 5th root. Can you think of a number times itself 5 times that would make 32? 2 works. And if you weren't sure, you would say, well, Parson, let's go back to that perfect nth roots. And you're like looking at power of what? 5. We'll go down to the 5th column here. Okay, the x to the 5th column. Does 32 show up there?
Yeah.
Right there. And if you go all the way over, what's the x value for it? 2. So the 5th root of 32 would be, we're talking about the 5th root, so we jump this x to the 5th, we're at 32. So backing up, 5th root would be what value? 2. Okay. 5th root would be 2. And again, if I wasn't sure, I could just check in the calculator. Say, is this a perfect 5th root? I don't know. Punch it in your calculator and see. If you punch in your calculator, you can see it's going to kick out 2. Right? Yeah. Punch the numbers in. Oh, you thought I was going to hit it. Okay. Okay. Guys, I think this is probably a good place to stop today. I'm going to pick this up with you when we get back from break because there's a lot that's going to happen in these next two examples. So, you guys have a good Christmas, okay? Me too.